This video lecture continues our discussion of model selection by looking at information criteria from a Bayesian perspective. To motivate our discussion, we'll first review model selection from a frequentist or maximum likelihood perspective, and then look at information criteria and how we can develop these information criteria using Bayesian analysis. So the model selections problem is viewed as a superset of the variable selection problem. So if you think of a regression equation, we might want to decide whether we include, for instance, polynomial terms or interaction terms. That'd be a variable selection problem. But we can think of it in a broader sense as trying to decide which of a number of models that we might want to use. Do we want to use, for instance, a linear discriminant analysis, a naive Bayes approach? Which of these models might be the most appropriate to use for our particular problem that we're working on? There's a great paper that was written some years ago by Cover, and he mentioned, the title for his paper was "The Two Best Are Not the Best Two." And this just indicates that it is very hard for us to do variable selection, much less model selection. And what he meant by that is that if we select the two best, given that we're looking for one-at-a-time selection, they may not in fact be the two that work the best together. So this is what frustrates the whole problem, is that we can't just go piecewise through our variables or through our models. We need to consider their interactions, and that's what makes it very difficult to do model and variable selection. This is also commonly referred to as a bias variance trade-off, and it's looking at two objectives, bias and variance. And this multi-objective problem means that we can never find one optimal solution. We're always trading off between bias and variance when we make selections. So some common approaches, again, from a maximum likelihood perspective. Within sample, for example, penalty approaches. These can include information criteria and bootstrapping. And as we saw from a Bayesian perspective, they can also include Bayes factor. The information criteria that we will develop from a Bayesian perspective in this lecture are also within sample category of penalty approaches. And then there are out-of-sample approaches. These are commonly used. As a data scientist, the most common tool is cross-validation, and to a slightly lesser extent, test sets. These are considered the gold standard for doing evaluation. The problem is that for really large data sets, we can't use cross-validation. It's just not practical to use. And test sets are viewed as one-of-a-kind sampling. So for a lot of reasons, these penalty approaches, particularly the information criteria approaches, are the ones to use in order to get a good model out of a number of different models. They're particularly popular now as we look at problems using deep learning, where we've got lots of parameters and lots of data, and we just can't do cross-validation. All model selection methods, whether they're within sample or out of sample, require performance measures. So to set up these performance measures and talk about how they're used in building things like the information criteria approaches, let's set the problem up the following way. Let y be the vector of actual n outcomes. So these are the outcomes that we observed for our problem space. Let y hat be the predicted vector given the data, which we'll use script D to represent. And we'll let the vector theta be the parameters of the likelihood. Then mean square error, a very common approach, is simply averaging the squared difference between the actual outcomes and the estimated or predicted outcomes. The mean absolute deviation is just the average of the absolute values of the difference between the actual and the predicted. The log likelihood just takes the log of the likelihood function of the response, the y's, given the data and the parameter values. And notice that unlike the first two, mean square error and mean absolute deviation, which we want to minimize, the likelihood is something we want to maximize. So we now have a maximization problem, but we can convert it to a minimization problem just by taking the negative of it. And for a lot of mathematical reasons, it's convenient for us to use a factor of 2. And we call this negative 2 times the log likelihood the deviance. So we want to minimize the deviance. All right, let's look at the information criteria that we can derive, particularly from these likelihood expressions. So to do this, let k be the number of parameters. Then we have Akaiki's information criterion, or AIC. This is perhaps the most widely used and well-known of all the information criteria and of all the penalty methods. It is the one that's most frequently used. It's used in tools, for instance, like stepwise regression. And it's just the deviance plus 2 times the number of parameters we have in our model. So for instance, if we have a regression model, let's say a main effects model with 4 variables, then we have 5 parameters, the 4 betas or parameters that are on each one of those variables, and the intercept, beta naught. So we would penalize it then by 2 times 5 or 10. It's a very simple criterion, but it works really well. There's another criterion which is often cited, and that's unfortunately called Bayesian information criterion, developed by Schwartz. It is really not Bayesian. It's only roughly or given a minor bit of justification through a Bayesian analysis, but it's really not a Bayesian criterion. You can see that it just takes the AIC, and instead of using 2 times the number of parameters, it now takes the log of the total number of observations that we have and uses that as the factor to multiply or penalize by the number of parameters. Well, we can extend these information criteria using Bayesian analysis, and that's what we'll look at now. So let's let theta hat Bayes be the posterior expected mean, and we're going to let k subscript DIC for deviance information criterion be the effective number of parameters, and we'll define that KDIC as twice the log of the likelihood given the Bayes posterior mean estimate minus what's shown in the second term, which is an average of theta, the parameters, over the posterior distribution. So let's see how we calculate that. We calculate it by sampling. So we're going to sample the parameters, and when we sample the parameters, we're going to get the likelihood, and then we're just going to average that over all the samples. And now we subtract that from the log of the likelihood given the posterior mean. And when we put that together with our Bayesian estimate for the deviance, we get something that looks very much like AIC, and it's called Deviance Information Criterion. This looks pretty good, and it works reasonably well, but it turns out that we can do better. So we'll do an even better job of estimating both terms in this information criterion. And the way we do it is for the first term, we compute something that's called log pointwise predictive density, or LPPD. And we calculate LPPD by first looking at the posterior densities at each of the sample points, and we're going to take the log of the product of those. And that then, if we do our typical trick, which is conditioning, and we will condition on the value of the parameter or parameters, and integrate that out, then we can compute the LPPD. But we don't actually do the integral. What we do, we compute again using samples. We sample from the posterior in this case. So we're going to sample from the posterior. We're going to call these samples theta S, and we then will average those values that we obtain from those samples of the posterior over every point in the observation space, all 1 through n. So we'll just sum up that. So we take the log of that average that we have from all of the samples, and then we sum up over all the observation points. That's log pointwise predictive density. Now we're going to again compute the effective number of parameters, but we're going to call this KWAIC for widely applicable information criterion. And that's going to be computed using the variance of the posterior. And again, we're going to sum that over all observations that we have in our data set. Again, this is going to be computed using a sample of the posterior variance. So we're going to sample the posterior variance. We're going to call that variance superscript S for each data point that we have in our observation space. And we're going to sum over all those data points. And that then is represented here. The KWAIC is just the sum of all the variances that we get from this sample over all the observation points. So we're going to look at the variance from those samples that we take, and then we're going to sum over all the observation points. Now, the question is, why would this variance be an indication of the effective number of parameters? Well, it turns out that the more parameters we have, the wider the variance. So by penalizing based upon the variance, we're effectively penalizing based upon large numbers of parameters. So this is doing very effectively what we want to do, which is penalizing our results for having too many parameters in them. So it basically is not a generalizable result. So we want to penalize that. And this KWAIC, using the variance in this way, the samples of the variance from the posterior, gives us a good indication of the effective number of parameters that we have in the model. So then the WAIC, or the widely applicable information criterion developed by Watanabe, is then going to be just the measure that we have for the estimate that we have for the deviance, which is minus 2 LPPD, or log pointwise predictive density, plus 2 times the effective number of parameters in the WAIC sense. And this then turns out to be a very, very good approach to using a information criterion to penalize our models and therefore allow us to choose the better model for our particular problem. And we can summarize these results here. WAIC, it's a relatively new approach, as you can see, developed in 2013, but already it's showing really good results in practice for regularizing models. It's easier to compute than cross-validation, so we don't have to go to full-up cross-validation to find it, which means that we can get this result just like we can get AIC. It's a little more computationally intense than AIC, but it's still easier to compute than cross-validation and therefore much easier to use for large data set problems. Another big advantage to it is it turns out that WAIC closely approximates cross-validation in the leave one out sense. So leaving one out and then validating with all the other terms and continuing through all the data points is an approach to cross-validation. Well, it turns out that WAIC closely approximates that result, which gives us a lot of confidence in what we're getting from the WAIC estimate. And overall, it's a good approach for Bayesian learning, but as we'll see in the next class, it's a very good approach for Bayesian model averaging.